Okay, we're going to go through number 1 on the 2018 AP Calculus BC for your response exam. Okay, so this is your classical rate in, rate out problem. And so for part A, when it asks you guys for how many people enter the line during the time interval, you're just going to integrate the rate at which they enter the line, because that is in, what is it? It's in people per second. Okay, R of t is in people per second, so if we just integrate it, we'll get the number of people. So for A, we are setting up the integral, and it's from 0 to 300, so from 0 to 300 of R of t dt, and it asks you to round it to the nearest, oh no, it doesn't. Okay, so you give your answer for that integral. So you integrate and you get your 270 people. Okay? Alright, then for part B, it's saying during the time interval from 0 to 300, there are always people in line for the escalator. How many people are there at time 300? This is a new equals old plus net change situation. Okay, so we're going to do new equals old plus net change. So the number of people at time 300, I'm just going to call it A for amount. So the amount of people at time 300 is going to be the amount of people at time 0, which is 20. There are 20 people in line at time 0, plus the net change, which is the integral of the rate of change. So it's the integral from 0 to 300 of rate in minus rate out, is how I would prefer to do it. Okay, minus rate out, I'm just going to throw it right inside the integral. Another option to this I'll give you in a second. Okay, and now this they ask you to round to the nearest person. That is also not true. Where did I see? Okay, this one I get 80. I'm sorry, guys. Oh, D. It asks you to find the nearest person on part D, and that's what I'm thinking of, and that's what I keep going to. Okay, I apologize. So, this one we're just throwing into the calculator. As a secondary option, if I don't want to write it this way, I can also say that my amount at 300 is my initial amount plus my net change in my rate in. Okay, R of t needs to be inside the integral because it is a variable rate of change. But if I want to, I can subtract rate times time. So my 0.7 person per second times 300 seconds that passes that they get off the line of the escalator. Because it is a constant rate of change, it is okay for it to not be inside the integral. So either of these purple lines will get you an answer of 80. Okay? Alright, let's move on to part C. Actually, before I move on to part C, I just want to emphasize that what we just found in part B is that at time 300, there are 80 people left in line. Okay? So we established that in part B, and now we're going to move on to part C. Okay, so for part C, it says for time greater than 300, what is the first time that there are no people in line for the escalator? Here's where it's really important to read what your equation for R of t says. It says between 0 and 300 seconds, this is the rate at which people are entering the line to get on the escalator. After 300 seconds, this is the rate at which people are getting online for the escalator. So after 300 seconds, my 300 second interval is up, nobody's getting on the escalator, okay? So to understand that after time 300, so for t greater than 300, nobody else is getting on the escalator, there's only people getting off the escalator. So if that's the case, I need to figure out what to do with this 80 people in line that are still there at time 300 that I found in part B, and if they're continuing to get off at a rate of 0.7 people per second, they exit the line at that rate, then how do I calculate how long it's going to take them to get off that line? Well, here's a great place where units are super helpful. I have 80 people in line, and they are leaving at 0.7 person per second, so people per second. Okay. So what do you do with those units? Because you want the first time would just be seconds, right? So if I want to get into seconds here, what do? Well, the best thing to do is divide your people per second. Hang on, divide your people by your people per second. And if you do that, you'll actually get your people, I did that, I'm getting a little too rambunctious with the letter P, times, instead of dividing by people per second, it's times second per people, right, when you do that division, and the peoples divide out, and I'm left with seconds, okay, which is perfect. So I'm going to do my 80 divided by my 0.7. Sorry, guys. Holy monkeys. I'm going to do my 80 divided by 0.7, and I'm going to get 114.285 or 286, depending on how you round it. But that's how many seconds it takes for the remaining 80 people to move on to the escalator and off the line. Okay, but it's asking what's the first time when t is greater than 300. So it's actually it's 300 plus the 114 additional seconds that it takes for people to finish getting off the line. Okay, so just be careful on that. All right, moving on to Part D. Part D is just your classic optimization problem that you guys have seen for pretty much every one of these, not pretty much, all of them. All of the rate in minus rate out problems. Okay, they require you to write a general formula for the amount of whatever it is at time t. So a general accumulation function for the number at any time t. So it says, when is the number of people in line a minimum? I'm first going to express the number of people in line. So I'm going to do new equals old plus net change, but instead of new equals old plus net change with a definite integral from 0 to 300, I'm going to do new equals old plus net change with an accumulation function. So my amount at any time t is my initial amount, 20, plus my net change in amount, which is the integral from 0 to whatever time I want to stop at, and it's rate in minus rate out here. Okay, it's always rate in minus rate out here. It is never anything but rate in minus rate out here. It seems consistent for like every problem set that we've done. So I'm going to do I can't put r of t here because I already used t as my variable in my bound. So I'm just going to make it r of x minus rate out. Okay, if you want to put rate out outside the integral, you're going to get the same answer. So some of you guys might have written, that a of t, sorry about that, is 20 plus the integral from 0 to t of r of x dx minus 0.7 times t. The only reason it's okay for me to pull that value outside the integral is because it is a constant rate of change. If I have a constant rate of change, it's your typical rate times time equals distance problem. So this is people per second, this is the number of seconds that have passed. It'll give you the total number of people that have gotten off the line because they've gotten onto the escalator. All right, either of these integrals give me either of these equations give me the amount of people at any time t. If I now want to optimize that, I need to take the derivative. All right, find my critical points, see where my derivative changes from positive to negative. So, my derivative a prime of t, the derivative of 20 is 0. If I look at the integral here, the derivative of an integral is the integrand, but with variable replacement. So it's r of t minus 0.7 with variable replacement. Okay. If I take the derivative on the next line, the derivative of 20 is still 0. The derivative of this integral is r of t. And the derivative of 0.7t is 0.7. So I'm going to get the same answer either way I write the original integral. Okay. So now I took my derivative, I want critical points. I'm going to set this equal to 0. I'm actually going to, in order for me to solve this equation, it's a calculator active problem, and it's not something that we can solve by hand. I'm going to graph this thing and find its x-intercepts. All right, so this is the graph of a prime of t, or r of t minus 0.7. If you're having trouble getting the graph to show up for you, just make sure that you've got the right number of parentheses, make sure you have a multiplication symbol in between the two big quantities that are being, one's I think to the third, one's to the seventh. I have to scroll up to see. But do that, and then you want to find the zeros, right, because we want the derivative to equal 0, so we can use the calculator or Desmos for that as well. And my first 0, so my first 0 is at 33.013, and my second 0 is at 166.575. Okay, so now just looking at this, one of the benefits of graphing like this, oh my lord, sorry guys, you're actually graphing the derivative. So you can even make a sign chart based on this picture that we have. So my derivative, a prime, I have zeros at my 33.013 and a 0 at 166.575. Now I don't need to make a sign chart, it's sort of moot point. But I can, and I can almost see the sign chart here. My derivative is below the x-axis here, before, from 0 to 33.013, so my derivative is negative, and then it goes above the x-axis, so the derivative is positive, and then this last portion, the derivative is below the x-axis, so it's negative again. So I can see I'm going to go from decreasing to increasing to decreasing. Is this stuff important? No, it's sort of a little bit of a waste of time, although it can help us minimize how much work we have to do with the next steps. If you'd like to consider this, that this is a local min, this over here is a local max. The reason that that's relevant is that you guys are asked for an absolute min. Okay, so I don't have to consider a local max as a possible absolute min, but because I do have multiple critical points, you have to check the values at critical points and endpoints. Okay, I really can't emphasize that enough. Because you have multiple critical points, you must compare the values of the function at critical points and endpoints. Okay, so I need to know what the value of the amount of people is at time 0 and time 300 critical points and endpoints. So those are my endpoints. The only critical point I have to consider for potential absolute min is that 33.013 time. Okay, because I cannot have an absolute min and a local max. So we're going to compare these three values. We plug it into our integral, so we know that a of 0 is 20. I know that a of 300, fantastic, I already did this. My a of 33.013 is going to be my initial amount plus my integral from my net change in amount, so my integral from 0 to 33.013 of rate in minus rate out. Again, I'm choosing to put it all inside the integral there, and I'm going to evaluate this integral using my calculator, and I'm going to get 3.083, and so therefore I'm going to conclude that the minimum number of people in line happens at t equals 33.013, and there are roughly 3 people in line at that time. Okay. All right.